All right, the first thing you got to understand here is that the photoelectric effect, the device that we're using for it is basically a light detector. It's an old one. We still use these though, right? There's a tube called a photomultiplier tube, which is a little bit more complicated. It's got many stages of this, okay? But it's basically a light detector, okay? This is how it works. Light comes in, it hits this metal, it ejects an electron. The electron, once ejected, notice that we've got this side negative, this side positive. Once it's ejected, it accelerates across, right? Because we don't want it to wander around in the wilderness, right? We want it to go zing and shoot across here, okay? And then we can detect that those electrons are getting ejected because we've got a very sensitive ammeter here, right? If the current is flowing, then there's light shining. If it's in the darkness, the electrons stay on the metal. There's a work function. Energy has to be conserved. They're not going to leave the metal spontaneously, but the light makes it leave, right? Okay. So when the ammeter reads as current, then electrons are being ejected, and there we go, okay? Now what Einstein said was, okay, let's take the same thing and let's change the polarity. Let's make this negative and this positive, right? So we're going to change our battery here totally, so that this is the positive side, and this is our negative side. Still, we're going to still be able to change the voltage continuously, right? Okay, but this is going to be the positive side, and this is the negative side, right? So now the electrons, when they're ejected, are going to experience a force that's driving them back to that plate. Why would they still cross this distance here? Well, they have velocity. They've got a kinetic energy. They're going to fly across. Of course, they're going to fly in random directions, but we're going to look at the ones that head straight across, right? Okay. So, what we have here basically is a force that opposes it, and ingeniously, he figures out a way to measure. It's now a method to measure the kinetic energy, right? So Einstein says, look, reverse the polarity. And now we can measure, we have a kinetic energy measurer. Now it's kind of a crappy light detector, right? Because if you apply the right voltage here, you'll keep all the electrons from going across, even if the light's shining, right? But that's not the purpose anymore, right? Now it's a kinetic energy measurer, okay? So his idea was this. Look, he said, look, if you set it up this way, then you can adjust this voltage here, and if you get a voltage that stops all those electrons, then that voltage, but just change it to electron volts, right? That voltage corresponds to the maximum kinetic energy of those photoelectrons in electron volts, okay? And then he said this, he said, look, this is the basic equation, right? Is that the photon energy, if photons exist, then their energy is going to turn into whatever that work function is, plus, in the case that you're stopping them all, that'll be the maximum kinetic energy, right? Okay. Then what he said is, okay, look, we know the work functions of metals. This is something that people understand. It's a basic chemical fact about metals, okay? You can look that up in a book. So what we have is this great way to measure this maximum kinetic energy, right? Which, everybody's like, great, Einstein, that's great. So what are you going to say about that? Well, what he said is that the maximum kinetic energy is going to depend on hc over lambda, because that's my prediction, that's my formula. Remember the Einstein's formula is that the energy of a photon is h times frequency, which is hc over lambda, right? Because of the wave equation, c over lambda is the same as frequency, right? So what he says is, look, if you do this experiment, you're going to get data that shows that maximum, here's how to measure the maximum kinetic energy, right? Nobody thought of that before. And if you do the experiment, you'll find that it depends on the wavelength. Everything else is a constant, okay? But if you do it with a bunch of different wavelengths, and this was a devilishly hard experiment to do, because you had to use metals with really, really low work functions, which, by the way, we're talking about like sodium metal here, right, which reacts instantly with air. So you have to do it in a vacuum, right? Okay. But if you do this with this experiment with many different wavelengths, you'll find that it depends on the wavelength. Okay. Now, wave theory Everybody knew, by the way, nobody had done this experiment, right? And everybody knew, oh, no, light is a wave, and light has these electric fields and magnetic fields, right? So if we look at a light wave here, we've got this electric field like this, right? Electric field up, electric field down. Now, by the way, there's a magnetic field that's at right angles to this that I'm not going to try to draw, okay? Also happening, right? Because changing electric fields make magnetic fields, and changing magnetic fields make electric fields, right? Okay, but let's just look at the electric field here, right? It's presumed maybe that the electric field tears the electrons off the metal, okay? Wave theory says, look, no, the maximum kinetic energy is going to depend on the intensity, okay? It's going to depend on the intensity, because the intensity this is a dim light, right? This would be a bright light, right? It's going to have a big electric field. Bright light has big electric field, therefore it's going to eject faster electrons, right? And it can't, of course, depend on the intensity and not the color, right? At the same time that it depends on the color and not the intensity, okay? So just a totally brilliant experiment, right? Einstein thinks of a way to measure the kinetic energy of electrons, predicts the result based on his theoretical model for light, and he's right. Not too bad, right? For some obscure patent clerk, okay? Now, what you got to understand, the secret piece here, this is the divulging, right? On the test, I'm going to ask you, how do you operate this? How do you operate the experiment, right? So how do you operate the experiment? How does one operate this experiment? Oh, how did the results? Well, the results were this, right? Kinetic energy did depend on the wavelength, and it didn't really depend on the intensity, and it was a mystery to Millikan, right? Okay, so now how do you operate the experiment? Okay, well, I tell you what, the first thing you do is you reverse the normal polarity. Yeah. You reverse the polarity of this so that this side's positive, this side's negative. We talked about this, right? So now the electrons, as they go across, are slowed down by the electric field. I don't know how many marks this question has, right? So maybe one mark is you reverse this polarity, right? Now you acknowledge that the electrons are now slowed down by the electric field. So now this voltage is a way to measure the kinetic energy of those electrons, right? Okay? And what you do for a particular wavelength of light, is you adjust this voltage from 0 to whatever voltage stops the electrons. Now, how do you know that they're stopped? Well, you read the ammeter. When the ammeter reads 0, okay, then you've stopped all of the electrons, okay? So you adjust the voltage upwards until the ammeter reads 0. Then you read the voltmeter, right? And the voltmeter tells you basically the electron volts of the most energetic photoelectrons, okay? So that would be how you operate this, okay? Brilliant idea. Okay, wow, I've just said all the words. So sorry about that.